Because of troubles with internet, I have to repeat some parts. So we will work with this group of lines. Yeah, okay, it is working. With this group of lines, we can use Atlas, this one, or I can use the spectrum, which is already identified. I have to activate white window, file load fits, and load. Okay, for example, this one. Yeah, it has wavelength calibration. Order 10, order 10. For identification, look, above we have wavelength calibration. Here we have no wavelength calibration. We have identification given in this form, but we can make our life easier if we use list of lines given in special format. Help, load identification, lin file, and we will use Toriargon, this one. Nothing happened because our spectrum, this one, has no any wavelengths, so nothing happened. But if we will repeat the same for this spectrum, load identification, okay. So we will use information from here for this spectrum. Free. Left button click, left button click. Free. Left button click, left button click. Now we are in main menu. We have to enter to the procedure creation of wavelength scale. Curve, dispersion curve workshop, create it, or just simply Control K. So we're in procedure make this hand is written. Okay, let's identify this strong line. I move mouse approximately to the center of line, not very important, F. Okay, and we have to enter wavelengths. Wavelength of this line 3873.8224. Why F? If you press F, program will find center of gravitation of the line. If you press E, program will put position of your identification at the same position where is your mouse at the moment. For example, here, now I press I, because of what insert I, and wavelengths 38, 40, 74, 24, 38. Okay, look, is incorrect. So for correction, you have to move your mouse approximately to the center of line, somewhere inside, and press B, binary B. And as a result, program will make reversed profile of the line. Because this line is symmetric, so you almost don't see any difference, but it's reversed. Later I will show you the difference when for asymmetric lines. So your goal is to match these two profiles. So now they are matched. Escape. How to? I move it using arrows, arrow left, arrow right. Speed of movement can be changed. So in default, speed is lowest. So one click, one press, one pixel movement. But if you select, for example, 3 is faster, 9 is maximum velocity, 9, 5, 1. Another way is when you approximately, okay, if you almost reach coincidence, just press A, because of word afterward automatic A. So it finds automatically the best position. But it works well only if line is symmetric. If not, it doesn't work and you have to adjust manually. When you find the best position, press escape. Yeah, ready. As you see, now it's moved to the proper position. The same we can do for this line, but I like position of this line. So we already have 2 lines identified. It means that we can try linear fit over these 2 points. Approach, save marks, approach, polynomial degree, only 2 lines, so degree can be only 1, not higher. So it means linear fit. Okay. Immediately we have identification list because we identified. We make because we fit, but polynomial degree 1 is not proper because shape of dispersion curve is much more complex. So in the closest line to the area of our fit, no problems. We see that almost perfect match, but for more distant, this match is very bad. So, but it's clear that this line belongs, this identification should be for this line, this for this one, this for this one. So just move mouse to the desired line and press F. Program automatically takes closest line from the identification list. If program takes it incorrectly, sometime it may happen. For example, for this line, if I press F, for this line, if I press F, it will take this because it's closer to the position. But correct one is this. So using these buttons, you can change identification wavelengths given in the used list of lines. But sometimes your line list is not complete. So in such case, you can remove this and put by hand what wanted wavelengths. Okay, in my case, should be this one. So let's check. Yeah, 38, blah, 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 is correct. 66, 33. Okay. Now I have 3 lines identified. And I can try F10 or approach is the same. Save marks, approach 2, higher polynomial degree. Yeah. And in this way, I can add many additional identifications. But now is faster way. F spacebar, F spacebar, F spacebar, because always it's correct. Full, all the spectrum. Let's work with this part. There is some displacement, so F, F, F space. Now again, approach, save marks, approach, 3, increase polynomial degree, full. You see, it's much better now, but not perfect. Let's add this one, F space. For zooming spectrum, we can use, as you can see, is full and free. Also, spectrum is divided on 5 equal parts. So 1 is most left part, 5 is most right part. Okay, from the beginning. And let's have a look on these weaker lines. F space. F space bar. Quicker zoom. I can press space bar and space bar again to return to the original scale. Space bar for zooming, space bar to return. F space bar for pressing OK. F space bar for pressing OK. F. This line is not good, but I select it because this defect doesn't affect too much on the position of my line. Well, second, F space, F space, F space, space, F space, F space, space, F space, F space, space, F space, space. Third range, F space, F space. This one, F space. 4, F space, F space. F space, F space. Full. Approach, save marks. Now we can use polynomial power 5. Okay, we see that some our identifications are not good. They are outlying lines. Let's check why. This one, hard to say. Let's remove it. It looks fine, but it's outliner. This one also good line in first view, but okay, let's remove. D. To remove, I press D because of delete. Just D. F10, 5. Okay, it's good enough. Pay attention to this. For BOES, sigma, or its average error, should be in the range 1 of 1,000, 1 part of 1,000 of angstrom. All wavelengths are measured in angstroms in this spectrum. So 1,000 part of, 2,000 parts approximately is very good precision, very good precision. Because for one pixel, we have this value, 0.2 approximately. And this error is 10th part of pixel, almost 10th part of pixel, very small. Okay, excellent. Excellent. Maybe it will help if we will adjust position of this using B. If I move mouse approximately to the center of line and press B, then move mirrored profile by arrow keys, escape. Yeah, now it's green. F10 or the same. It is the same as clicking approach. I can press F10. Enter, enter, 5, enter. No big difference. But anyway, I tried. Okay, one order is identified. We have to identify at least one order more. So this order number 11. Here also I press tab to change order. So also order 11. Again, let's use this specific group of lines. Specific group of lines. Yeah, you see difference. This line has a defect on the center. Actually, it's connected to the fact that this spectrum was overexposed. So this effect of saturation. And actually, such lines should be not used for any purposes. Okay, we have to identify. Again, I activated our spectrum curve, dispersion curve workshop, created. Let's take this line. F 38, 40, 74, 8, 6, 1, 9. Enter. And maybe this line. F 38, 74, 24, 24, 38. Yeah. Now I can try to approach, save marks, enter, just one. Immediately we have additional lines, F space, F space, F space. Actually, this is very good example, a good example of asymmetric line. I will show you what happens if we try to match, to find x of symmetry for asymmetric lines. Okay, B, look, now we have reversed or mirrored profile of the same line. So we have to match to find central middle point of the line in some place, because line is asymmetric. Middle point always is in different places. For example, in this level, in the level of cursor, I match it, so middle point is here. In the upper part, middle point, in this part, middle point is here. So my recommendation, if you work with asymmetric lines, normally you should match lines, mirror profiles and original profile, not in the top of line. We call this place core of lines, but in the point which corresponds approximately 70–80% of intensity. So somewhere here. Why? Because upper part always is affected, not always, but frequently affected by some different effects. So it's more precise to use this additional noise maybe. But sometimes, of course, core part is better. Maybe right now core is better. But okay, let's try follow to my recommendation and use this 70% level of intensity. Escape. So we matched this line, F10, enter 2. Yeah. Now it's hard to say. Okay, free. Peak displacement because extrapolation is very strong. F space, F space. Let's repeat fitting. F10, enter, enter. 3. 3 may be too much, but okay. I already put 3. Here, it's even not clear. I think this one is this line. Space for zooming. F space to press OK. Ready. F10, enter, enter. 3 again. Yeah, much better. 1. Let's add these lines. F space, 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 F space, 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 F space, space, F space, space. Okay, let's try F10, 3. Yeah, it's good. Not good line, but I always try to identify lines where closer to the border of spectral order, because extrapolation is always bad thing. Much better to avoid a lot of extrapolation. But quality of this line not so good. We can try F space. I added. So second part of spectrum, space, F space, F space, F space, F space space F space F space space. I'm not sure. F10, enter, enter, 3, enter, enter. Yeah, now I'm sure which one is what. F space, F space. This line is very asymmetric with very long wing. We call this wing. F10, enter, enter, 3. Okay, part 2, part 3. This line is too strong, very broad, so better to avoid such strong lines. F space, F space, F space, F space. I'm not sure that F will work well in this case. Why? Because F works with gravitation center, but we have here additional unresolved line, which is affecting to the position of this vertical line. I think it must be somewhere here. So B, and now I adjust here. I would like to adjust exactly top of the line, escape. Yeah, it's moved to the position which I prefer, 3. Very broad, better to avoid. F space, F space, F10, 3, 4, F space, 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 5. As I said, maximally closer to the edges. Signal to noise on the edges always is lower, so lines are affected by noise. F space, F space, space, F space, space, F10, enter, enter, 5. Sigma still is 1, okay, now it's 5 multiplied by 1,000th part, so it's good enough, good enough. Still much lower than wavelengths for 1 pixel. I like it. Maybe we can add something here. F space, F space, F10, enter, enter, 5, enter. So we have 2 orders identified. Yeah. Now we can try to arrange so-called global fit curve, dispersion curve workshop. Here we have DCM info. What means DCM info? All our manually set positions, so-called marks, all these marks are stored in, yeah, we are working with this file 38, so this DCM, in DCM files, in binary format, of course, but if you press curve, dispersion with DCM info, it will show you what's going on with all your spectral orders. All buttons are gray if no identification, they have no any marks, but we have put some marks for order number 10 and number 11. 2 orders are identified, just to know. Directly from this place also you can go to some desired order, for example, order 45. Look at this, 45. Curve, again curve, global fit. Here, global fit. Global fit, what means global fit? It means now after, before this function, we made fit for each order separately. This fit based only on pixels for one order. Now we will try to make two-dimensional fit, which includes not only pixel space, but also order space. So by X, when we have identified only two spectral orders, I would like to reduce polynomial power. We already know that at least should be 5, but we will try 3. And by order, we have only 2 orders, so this power must be 1. We cannot put higher than 1. And try iterations. At first, let's try just one iteration, global fit. So what we have? We have global fit, so-called. It means that we have order 10, its points in pixel space. We have 3 graphics. In the upper, we have difference between our wavelengths entered for each hour mark and between wavelengths obtained after global fit. So error is very small. Error is very small, and it's seen from the shape. And order 11 also is excellent. Second graphic shows the same in an order space. So horizontally, we have orders. Look what happens here. This corresponds order 10, order 10, order 11, but we have nothing more. Here, somewhere here should be order 84, somewhere here should be order 1. And this is global graphic, last one, in the wavelength space. So shortest wavelength space, which we have now, 3,800 with something, and the longest 3,900 only, very low, just 2 orders, so very narrow part of spectrum. Okay, let's try to apply our global solution for other spectral orders, right? Yes, yes. Okay, let's return to our order 10. In order 10, nothing changed, so our global solution not affected our local solution when we try it. So all identifications are in the same places, in correct places. This is order 11, also the same, everything is okay. Let's check what's going on with next order, 12. You see, in order 12, our solution is well working, and we can easily add our spectral lines just by F. But this is very close to our already identified orders. What situation in the bigger distance? For example, let's go to the order number 1. Even in order number 1, situation is not so bad. It's not so bad. And let's go to the order number 30. Even order number 30, but in number 30, not so good, not so good. But we can understand, we can understand why, and we can recognize proper identification. So there is some displacement on the edges, Okay, let's try Control K. Now we're in make this hand procedure, and starting from the first part of the spectrum, we try to add identifications F space, F space. Later we will return here. F space, 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 This asymmetric, so I will not use it. Here is displacement is severe. F space, F space, F space, F space, F space, F space. Okay, approach. Let's try order 5. Yeah, it's good. F space, full, 1. I don't like this displacement. So we have to add the more. Yeah, right. This one. F10, 5. Yeah, much better. F space, F space. This one is weak. Look what happens if I will try F space. Absolutely incorrect. So B and I match mirror profile. Yeah, now it's good. It's just example. F space, F space, F space, F space, F space. Ready. F space, F space. Ready. F space, F space, F space, F space, F space. Full. F space, F space. Full and this area. More line, higher precision. More lines, higher precision. Also, should be not big empty spaces. If possible, always bad lines. Why bad lines? They are symmetric and very strong. Okay, let's try. Ooh, yeah, very asymmetric. No, D, remove. This line, F space. Looks better. F10, enter, enter, 5, enter. Not so bad, not so bad. Okay, so we have now 3 spectral orders identified. We can try increase this by order for 2, iteration 1, global fit. Now we have 3 spectral orders. Looks okay, okay, right, and exit, okay. Let's check order number 1. Excellent coincidence, almost excellent, but good enough anyway. Let's go to order 60. There is problems, but we can say correct positions, recognizable. Okay, let's make this order. Control K, quickly, F space, F space, F space, F space, F space, F10, 3, full, yeah, F space, F space, F space, F10, 3, this area, F space, F space, F space, full, F space. This line is useless because it's crowded and corrupted. It's corrupted because of saturation. Also corrupted. F space, corrupted. Shifted, strongly shifted. Okay, let's try this one. Look what's happened. 85, 34. Yeah, it's correct. F space is corrupted, but this one looks good. F space full. F10 enter 5 enter. Okay, excellent. Free. F space F space F space F space F space F space F10 enter 5. Excellent. How many orders we have already? 4, if I'm not wrong. Yeah, let's try 3, and now we can try 5. Iteration, let's put 1. Excellent, excellent. Right. Yes, yes. So step by step, we increasing quality of our dispersion curve. Let's check our order 84, last order. What's wrong? Is it? No, order number 1, everything is okay. Let's go to the order 80. Actually, it looks okay. Let's identify. Oh, I'm not sure about it. I'm not sure. This three lines we can find. Control K, F space, F space, F space, approach, save marks, approach. 2. 3 lines can be approached by polynomial power 2, F space, F space, F space, F10, 3, 1, 1, F space, F space, this group of lines, F space at least, F10, enter, enter 3, yeah, excellent. So F space, F space, F space, F space, F space, full, F space, full, F space, full, 5. This is very bad line, corrupted, but this one is okay. Is okay. Is okay. Full, 3, F space, F10, 5. Okay, I like it. I like it. Here maybe let's add this one. This is corrupted. F space. What more? Corrupted. It's already added. This one corrupted. It looks like we cannot add anything more. Escape. We are in main menu. Dispersion curve. Global fit. Global fit. Good. All right. And exit. I think this is the last step. So now we have no any extrapolation, only interpolation, and in all of cases, matching almost perfect in all spectral orders. Go order 1, practically perfect. So our goal now is estimate weakest line which can be used for identification. I think level about 2000 is acceptable for weak lines. No, 5,000 is here. So 5,000. Okay, let's try 5,000 as a limit. Now, Control K, make this hand. I press right button of the mouse and sorry, no, I press L, load L. We have another window, and in this window we should spectrum as emission line, yes, as mission type. Don't move existing mark, yes. Processor for all orders, yes. Keep orders with existing mark, yes. Don't touch them, don't add anything. Emission minimal intensity to be considered. Okay, try 5,000. Start. Okay, curve dispersion workshop DCM info. Look, all orders have something. Okay, except this one. Page Y. Okay, maybe our identification list has no lines in this area, perhaps. Okay, doesn't matter. Let's go. Insertion tool workshop global fit. Let's try all these parameters. I like it actually. I like it. Okay. Okay. Now increase number of iteration to 20. It means that spectra will be okay. Fit will be repeated many times. Each time program will determine if are some marks which are exceeding this 3 sigma. We can change this 3 to 4 or 1.5 is the lowest possibility. The so-called sigma clipping algorithm. By default 3, and I don't recommend touch this, change this. So 5, 3, 20. And when program will find situation when no new marks should be removed, iterations will be stopped. Or if not, if it reaches iteration number 20, it also will stop. Okay, let's try this way. So we see that after 12th iteration, process stopped, and we see almost perfect view. But now we have this sinusoidal shape. It means that we have to increase polynomial power. For example, let me show what happens if you put incorrect value by order. Okay, I reduce this to the one global fit. Yeah, not okay. Let's try at least 2 global fit. You look, you see this. It has some curved shape distribution of spectral orders. So at least 2 or even 3 might be used to also see some shape. Perhaps 3 is better. Global fit. Yes, I like 3. I like 3. Okay, again, what happens if we put here also not value is too low? You see, you have some pattern. Should be just cloud of marks, but we have some shape. It means that our polynomial power is not sufficient. Global fit is 5. Better, again, 20 global fit. And now we have this one. Actually, this is acceptable because you see, finally, we reached a very low value of error. Very low value. Okay, let's accept this. But later I will try to check what's going on with this program. And additional possibilities. You can check distribution of identification marks in for each spectral order. For example, order 25. Look, in pixel space, in order space, and in wavelength space. Here, okay, wavelength space. Okay, so next step, we have to apply our wavelength solution to all spectra in our data set using this one. Check it and using the left button of the mouse, select files, right, and exit. Okay, right, and exit. Finish.